So this is going to be a video on how to apply the extreme value theorem to find global min or max, or absolute min max, same term, different terminology, same idea, for a function on a closed interval. According to the extreme value theorem, since we have a continuous function, meaning there are no asymptotes or gaps in the graph, cubic function, it's going to look something like that, right? It's a smooth curve. You could draw it with one stroke of a pen or pencil without having to lift it up to draw the whole thing. For example, no asymptotes. So we have a continuous function defined on a closed interval. The endpoints are included. That means we are guaranteed to find both a global min and a global max. In this example, though, we'll focus on the maximum. We won't worry about the minimum too much, although we'll end up kind of finding it along the way. So in order to do that, I need to find the critical numbers because according to the extreme value theorem, the places where I might get the maximum, the global max, is the critical numbers or the endpoints. So I need to find the critical numbers. So step one, I'm going to find the derivative, f prime of x. And this is a pretty simple function, just a cubic. We just need the power rule, so this isn't very hard. So 3x squared minus 8x plus 5, right? And then step two, I need to find out, based on that derivative, where are the critical numbers. And there's two parts to that. Part one, I need to look for where is f prime of x undefined. Now when I say where, I mean what x coordinates. And 9 times out of 10, this won't get you anything because for most functions, this isn't going to happen. But you have to check because the 1 time out of 10 where it is relevant, if you're used to glossing over it, you'll forget to do it. So you need to check every time. This is a cubic function. I'm sorry, rather, the original is, but the derivative, this is a quadratic function. So we're looking for where is this quadratic function, the derivative undefined? Well, are there any numbers that when plugged in for x, result in no, you don't get a result. Either you're divided by 0 or you have the square root of a negative or something like that where you don't get a result. In this case, no. For a quadratic, any input will be fine. The domain of the derivative function is all real numbers. So nowhere. You get nothing from that part of step 2. But it's an essential part you have to check to be sure. So the next part is we need to solve the equation 0 equals 3x squared minus 8x plus 5. I'm looking for where's the derivative 0, okay? Because at a critical number, you might have a local min or max where you have a horizontal tangent line. Well, that's what we're looking for. Where's the tangent line horizontal? Okay. So I just made up these numbers without thinking about them too much, but I suspect we're going to luck out and that this is going to factor. That was not intentional. So if it doesn't factor, we'll use the quadratic formula, but I suspect this will. I think this is going to be 3x minus 1 times x minus 5. And one way I like to check this is I multiply... Oh, no, that's not going to work, is it? Okay, maybe it won't. Well, let's do this. That's not going to work. That's incorrect. So... Right, that's not going to work. That's fine. You try it out, it doesn't work, that's fine. We'll use the quadratic formula if we have to. And the other thing I can do is I can use the AC method to try to factor. The number 15 factors as 1 and 15, but also 3 and 5. Negative 3 and negative 5. Okay, wait, so it does factor. I was just doing something wrong. Okay, my mistake. 3x minus 5 minus 5 times x minus 1. There we go. So it does factor. My mistake. So now I'm going to separate these two factors. Whenever you have an equation where you have a product that results in 0, 0 equals something times something, that means at least one of those somethings has to be 0 for some x value. You don't know up front what it is, but you're going to find the x value. So for this first equation here, I'm going to solve by adding 5 to both sides. So I get 5 equals 3x, and then I will divide by 3. So 5 thirds equals x. Getting ahead of myself. And then on this other equation, I'll add 1 to both sides. So I'll get 1 equals x. So I find my critical numbers are x equals 1 and 5 thirds. And I'm not going to get a decimal number. I'll leave this as a fraction for now. So step 3 is I need to apply the extreme value theorem. And I'll abbreviate the EVT, extreme value theorem. Okay. Now this differs from the first derivative test in that we're not going to make a number line, we're not going to pick test points. I just need to check at the endpoint values 0 and 2, and the critical number values 1 and 5/3, which of these has the greatest result from plugging it into the original function. So I want to look at what is f of 0, and then what is f of 1, what is f of 5/3, and what is f of 2. But I'll start with f of 0, what that is. So, look at my function again. So 3x, so x cubed, so 0 cubed minus 4x squared minus 4 times 0 squared plus 5 times 0. Okay, so that's of course going to be 0, right? Okay, so now f of 1, which won't be very hard, this is 1 cubed. It's not very good 1, let's fix it. 1 cubed minus 4 times 1 squared plus 5 times 1, right? So that totals up to 2, I believe. 2 minus 4 plus 5. I'm sorry, 1 minus 4 plus 5, which is 2. Okay. So now I can do f of 5 over 3. Okay. This one's going to be a bit more of a pain. If you need to, you can use a calculator, but I'm going to do this manually, I think. Plus 5. 5/3. Okay, so 5 cubed, that's 125 over 3 cubed, which is 27. So the numbers are a bit messy. And then I get 20 over, I made a mistake here. I didn't write that this was squared. Okay. Squared, okay. So I get 25 over 9, but I'm multiplying by 4, so I'll have 100 over 9 plus 25 over 3. And again, it might be tempting to go to a calculator, which, that's fine. I'm just going to do it manually. So both of these fractions need to be scaled up. They don't have the right denominator. So in the first case, I'm going to multiply top and bottom by 3. Top and bottom by 3 to get 300 over 27. And then in this case, I'll multiply top and bottom by 9, so I'll have 225 over 27. So I get 125 over 27 minus 300 over 27 plus 225. Someone can check my arithmetic there. I'm pretty sure that that's right, pretty confident on that. So when I combine these, if I combine 125 and 225, I get 350, right? And then minus 300, so I'll get 50 over 27. And this is a little bit less than 2. We do ultimately need a decimal approximation. I don't think I have a calculator on this iPad, so I'm just going to pull one up I have handy here. Just give me a second. 50 over 27, not 52 over 27. Okay, and I get 1.8519. Okay, so I've got three results. I got 0, I got 2, and I got 1.8519. So far, the largest result has been 2. I got 0, 2, and 1.8 and change. 2 is the highest so far. But I still need to check f of 2, because maybe that's higher still. So f of 2, that's going to be 2 cubed minus 4 times 2 squared plus 5 times 2. So that's going to be 8 minus 16 plus 10. All right? And that's also going to be 2. So when x is 2, the output is 2. When x is 1, the output is 2. So I have 2 x coordinates tied for having the greatest output. So our global max value is 2. And it occurs in 2 places, at x equals 1 and x equals 2. Okay, so we get 2 places that occurs. So basically, if I do a quick sketch for you, sometimes it's good to see a picture of it. And I don't want to pull up Desmos right now. I'll just do a quick sketch, graph, something like that. And these 2 high points, they're it's a little off. They're tied for first place. They're both at height 2. Okay, so that's roughly what the graph looks like, just to give you a visual idea of what it looks like. So, in a later example, later video, we will apply the same technique of using the derivative and then finding the critical numbers and then applying the extreme value theorem. We'll apply that to an application problem so it's a little more tangible and you can see why you would care to do that besides just math class.